go here and study cylinders now. Cylinders come into contact. So yeah, what I was discussing is that we're going to look at cylinders coming into contacting bodies. So now in this case, I have two cylinders coming into contact. That contact now is going to have like a line. So they're going to come into a line, but not a line anymore because we said that we're going to allow these bodies to elastically deform. So now instead, you're going to get a rectangle of width 2a and length L. L is the length of the cylinder, and the width of the contacting rectangle is going to be 2a. Again, when you have two cylinders coming into contact, if they're perfectly rigid, then it will be a line, but because we're allowing them to deform, it will become a rectangle. And that rectangle has a width 2a, you can see that here, 2a, and then the length of the cylinder is L. The maximum contact pressure is given by this formula, P naught equals 2F divided by pi AL, where L is the length of the cylinder. The width of the contact is provided by this formula, half of the width. Obviously, this is half of the width. I told you the full width is 2a. So this is half of the width. And you can see that it depends on the modulus and the Poisson ratios as well. I'll pause there for a couple of seconds for it to sink in. Again, I don't recommend memorizing these formulas. Rather understand what they mean, because that's where you're going to learn the most, is understanding the meaning and then applying it successfully for various different problems. Any questions so far on this particular cylinders coming into contact? No questions on that, so I'll continue. And very similar to what I had discussed before, you can calculate the principal stresses, sigma 1, sigma 2, and sigma 3. They're generated along the z-axis, and the z-axis is going to be at the contact point, starting there and then moving deeper into the material. Again, it does not depend on the modulus of the material. You can see that there. It depends only on the pressure, the max pressure, but also depends on the Poisson ratio. The max pressure here is the max pressure caused by the two cylinders coming into contact. Sigma 1 is provided by this formula, but now you realize here the sigma 2 is different. It's not like the sphere problem where sigma 1 and sigma 2 were equal. So in this case, you have a different answer. Sigma 3 is also different and is given by this formula. And now you can calculate the max shear stresses, which is where you take the max principal stress minus the lowest value of principal stress divided by 2. Now I can plot the von Mises distribution, and what you see here is that the highest von Mises stress occurs deeper into the material, and then also the shear stress is deeper into the material. So therefore, the failure is likely to initiate just below the contact surface, not at the surface. If the body of material behaves brittle, like some ceramic materials, if you have a ceramic behavior that's brittle, and the ball or the cylinder was brittle, in those scenarios, you're going to have the failure criteria that most likely is applicable is one where you have a max principal stress. And that's going to happen more at the surface of the material, where you have the highest stresses. So again, one more time, if you have a ductile material, it's likely going to fail following more of a von Mises situation. While if you have a brittle material, it's going to likely fail more at the surface, initiate at the surface, such as a brittle material, and max principal stress is a better measure of that. Any questions so far about that? I'll then continue then and study the situation where you have two parallel cylinder rollers, but now what I'm showing you is the deflection associated with that. So the same formulas I showed you before, I'm just giving you the deflections now, which I did not provide to you. There's some interesting functions here, logarithmics showing up here, as you can see. And now we can look at special cases where the modulus of the two materials are the same. And if you have that situation with the Poisson ratio 0.3, for that special case, you get pressure being equal to this, the max pressure being equal to this, and then the contact area or the width, half the width, because the full width is 2a, that's half the width here provided. What about other two cases where you have a cylinder on a flat plate or a cylinder in a groove? Again, cylindrical groove. In that case, again, you will now use this very formulas I provided to you earlier and set one of the radii to infinity for the one for the flat plate. Because if you do that, then the radius of curvature becomes basically a representative of flat plate. So looking at that situation, I have a cylinder now on a flat plate. Again, it forms a rectangular contact zone. I'm going to assume both of the materials have the same modulus. I'm going to assume the Poisson ratios are the same. And I'm going to choose one of the radius to go to infinity to effectively simulate the fact that the cylinder is on a flat surface. And if I do that, I invite you to check that what I get is this max pressure and then this max half of the width contact width, sorry. So it's half the contact width, if you recall. The A. So just to show you the picture again, the width is 2A of the contact area. It's a rectangle contact area for two cylinders coming into contact. What is the consequence of contact? You're going to have pictures like this, where you have some pitting going on, goes deep into the material for metals. For ceramic or brittle materials, it may be more superficial that can go deeper and spall material out. So that's a different situation. In this case, contact stresses can cause fatigue in some bulbs, as raceways, or even bulbs that are rotating around the raceway. So the effects of materials combination should be considered in the design process. As you mentioned, the maximum contact pressure between two curved surfaces depends on the types of curvature you're using in your design, the radius of curvature used in the design, what's the magnitude of the contact force, and then what are the properties of the two materials coming together. Through careful material pairing, then you can optimize and get the lowest contact stress for that particular application. Let me give some examples next. Any questions so far?